Hi, I'm Alice, a developer relations engineer on the Android framework side. I'm here to discuss how to optimize your app battery using the Android Vitals wake clock metric. In this video, we will cover the following topics: the new core Android Vital metrics in the Play console, best practices with wake clock usage, and how to debug excessive wake clock usage. App Vitals in the Google Play console serves as your essential tool for monitoring and enhancing the technical health of your applications. You can get to the Vitals from your overview page in your Play console. Historically, the most important metrics in the App Vitals, the core metrics, have been focused on stability, with user-perceived crash rate and user-perceived application not responding, ANR rate, being the most important indicators. This year, we made some updates to the core App Vitals definitions to also include metrics that contribute towards high battery drain. On Wear OS, we have introduced an excessive battery usage metric. If you're interested in learning about how to avoid excessive battery usage on Wear OS, one of the best solutions is by adopting the watch face format. Check out our blog on it. The recommendations around wake clock usage will also apply to Wear OS applications. What we'll focus on for this talk is the mobile device metric. We have introduced the excessive partial wake clock metric to the general audience, recently leaving beta. Android Vitals considers partial wake clock usage as excessive when wake clocks are held for at least 2 hours in a 24-hour period. This applies to non-exempted wake clocks acquired while the screen is off and the app is running in the background or running a foreground service. Excessive usage is flagged if it affects more than 5% of your app sessions averaged over 28 days. Now, you may be wondering, what is a partial wake clock? A wake lock is a mechanism that allows an app to keep the device's CPU running even if the app user is not actively interacting with it. A partial wake lock allows the CPU to keep running despite the screen being off. A full wake lock, however, keeps the screen on as well. If partial wake clocks are used excessively or improperly, they can lead to significant battery drain. For example, we've seen scenarios where apps have chosen to hold a wake clock for hours at a time or did not properly release the wake clock, leading to frustrated user reviews calling out battery drain. There are two methods partial wake clocks are acquired. The app manually acquires and releases the wake clock using WorkManager APIs for a specific use case. Often, this is acquired in conjunction with a foreground service, a platform API intended for user-perceptible operations. Alternatively, the wake clock is acquired by another API and attributed to the app due to the usage of the API. You might actually be surprised to hear that even if your app does not contain any code to acquire and release wake clocks, the app can still be deemed to have excessive wake clocks due to usage of these APIs. Let's do a short round of wake clock trivia. Feel free to pause the video to consider your answer. We will go over several use cases, and you need to decide if any of these use cases would need to manually acquire a wake clock in order to execute in the background. If not, what is the alternative API that you should use instead? First, schedule a periodic sync in the background to download fresh content for offline viewing. A manual wake clock is not needed in this scenario. When you're executing a worker or job using the task scheduling APIs, WorkManager or Job Scheduler, a wake clock is held by the system on behalf of the application while the task executes. WorkManager is a Jetpack library that relies on the platform API Job Scheduler to schedule jobs that keep the application alive and hold a wake clock while the task is executing. This is why you would see wake clocks with the name job associated with workers. Playing audio in the background. Manual wake clocks are not needed. When an audio track is playing, the system automatically acquires a wake clock attributed to the app. Note, system-held audio wake clocks are exempt from the excessive wake clock calculation in App Vitals. Communicate with an external device via Bluetooth. Manual wake clocks may be needed. Since there do not exist Bluetooth APIs that hold wake clocks during Bluetooth data transport, the app will need to schedule a task using WorkManager or run a foreground service and manually hold a wake clock if communication should happen while the screen is off. Finally, listen for location updates. Manual wake clocks are not needed. When new location events are received using Fuse Location Provider Service or Location Manager, a wake lock is held to alert the device for a brief period of time. However, manual wake locks may be needed to process the location events. This nuanced information is also available on documentation called Identify Wake Locks created by other APIs. Before we move on to debugging wake lock usage, let's go over 4 best practices you should consider. Have you considered alternative wake lock options? We can use this handy flowchart from the wake lock documentation to help us decide whether or not to use a partial wake lock. Does the screen need to stay on? If so, what you're looking for are APIs to keep the screen on, not a partial wake lock. Is the application executing a foreground service? If not, you do not need to manually acquire a wake lock. Is it detrimental to the user experience if the device were to suspend during this action? For example, updating a notification once the user has woken their device is not a task that should require a partial wake lock. If it can be detrimental to the user experience, such as communication with an external device, then let's move on to our final question. Is there already an API, such as WorkManager or Fuse Location Provider, that can keep the device awake on your behalf? Using task-specific APIs that handle wake locks for you is a great way to avoid bugs and make your wake lock usage as efficient as possible. You should only be acquiring a wake lock manually once you've gone through all of these questions and arrived at the manual wake lock answer. Suppose you do reach the decision to manually acquire wake locks. You should also confirm if you're naming the wake lock correctly. Make sure to leave out any personally identifying information in the name, such as an email address. If the device detects PII, it's logged as unknown instead, which makes it difficult to debug. Don't name your wake lock with the class or method name programmatically. If you try to get the name programmatically, it might get obfuscated by tools like ProGuard. Instead, use a hard-coded string. Don't add a counter or unique identifiers to the wake lock tag. The code that creates a wake lock should use the same tag every time it runs. Doing this makes it easier to detect abnormal behavior because it enables the system to aggregate wake lock usage by name. When acquiring wake locks manually, ensure that the wake lock is always released. Here's some code I've written acquiring and releasing the wake lock after doing some processing. But upon further inspection, the wake lock could never release in this scenario. Can you guess why? The issue is that if an uncaught exception is thrown, the wake lock release will never execute. Instead, I should do something like this, where I have a try finally block to ensure that I always release the wake lock even if an exception is thrown. Another thing you could do is add a timeout to the wake lock to ensure that the wake lock always releases after a certain period of time. Finally, in scenarios where you are requesting data periodically, think about whether you can reduce the frequency of wake-ups. For example, you can reduce wake-up frequency when using WorkManager by increasing the periodic interval between periodic work requests. When polling for sensor data using Sensor Manager, you can reduce the wake-up frequency by leveraging the batching mechanism. This is done by specifying the maximum reporting latency when registering the listener. Similarly, with Fuse Location Provider, you can use the method getLastLocation to get the recently cached location. Use setPriorityPassive to specify a less battery-heavy update mechanism, or leverage batching by setting a minimum update interval. There are times, even with our best intentions, we still arrive at excessive wake lock usage. If your app has been alerted, let's go over how to debug this. Your App Vitals dashboard may look something like this. You'll see a warning that tells you Play has found that your app has excessive wake lock usage. So what now? We're going to run through 2 scenarios based off of real-life examples where we've seen developers encounter excessive wake locks and talk about the tools to debug these scenarios. The first will involve a simple scenario involving updating the weather. The second is a more complex scenario with a health app. In this first scenario, I've built a weather app that periodically updates the weather to display in a widget or notification format. The App Vitals Excessive Partial Wake Lock dashboard will look something like this. I'm able to see that 11.59% of overall sessions are deemed excessive, which greatly exceed the 5% threshold. When I scroll down further, I'm able to see a list of all non-exempted wakelock names associated with this app. In this scenario, I have a wakelock name called Job, package name, System Job Service in the Android X Work package. Previously in our quiz, we talked about how WorkManager uses Job Scheduler, which acquires a wakelock attributed to the app. This indicates to us that the workers created using WorkManager are likely the culprit of the issue. By the way, we recommend upgrading your WorkManager version to 2.10.0 and above, which will ensure the wakelock tags are more verbose. For devices running on Android 16 and above, the worker class name will be included by default. I've already tested several flows manually on my device, and I'm going to spin up a debug instance of my app and use a tool in Android Studio called Background Task Inspector. To do that, I should do the following. Select View, Tool Windows, App Inspection from the menu bar. Select Background Task Inspector tab. You should see a list of workers that have either finished execution, are in the process of executing, or are pending. You can click on a worker that you want to inspect further to see the full details of the worker. In this instance, I'm seeing that Weather Sync worker seems to have failed and has retried frequently. I can also click on the graph under Worker Continuation to understand the worker chain and what kicked off this worker. The worker may be retrying often for a number of reasons. For example, if a job runs for longer than 10 minutes, it will begin to time out and will be rescheduled to be executed at a later time, increasing the retry frequency. For this particular use case, it doesn't make sense for the worker to retry so often, so I'll need to debug exactly why the retries occur. For debugging in-field issues with excessively running workers, I can also use the API getStopReason available in WorkManager 2.9.0 and above and in Job Scheduler on API level 31 and above. Here's an example code snippet using WorkManager where I've used Kotlin flows to log the stop reason on a specific work request ID. In my example scenario, when I check the logs for this worker, I will see a high percentage of stop reasons that are associated with the stop reason timeout or quota, signifying that this particular worker is frequently stopping due to exhausting the runtime duration granted by the system. Using this information, I've been able to find an edge case that caused excessive worker duration. While the tools I mentioned are helpful for debugging wakelock usage with workers, they cannot help debug manually held wakelocks or other system-held wakelocks. In scenario number 2, we're debugging an app that is much more complex. There is location tracking, Bluetooth communication, and usage of device sensors. Here's another wakelock dashboard with a breakdown of non-exempted wakelock names associated with the app. Apart from WorkManager, some of the worst wakelock sessions in this scenario are named Health App Sensor Wakelock, Health App Location Wakelock, and System Foreground Lock. Note that the exempted wakelocks such as audio or location-related wakelocks are not visible here. In order to debug these particular wakelocks, we're going to record a system trace. A system trace is a powerful debugging and performance analysis tool that allows developers to capture a detailed record of system activity over a specific period. There's a lot of various information that a system trace can cover. Let's go over a few of these. CPU activity to understand changes in the CPU cores and their states, such as switching between running and suspend state. Thread activity, which can help you understand multi-threading in your app. Network activity to understand when network packets are sent and received, which can be a high contributor to battery drain, and battery-relevant metrics such as job duration and wakelock usage. There are many different methods to capture a system trace. For example, using the System Trace command line tool, the Android Studio CPU profiler, or the Perfetto UI. You can also choose to record a system trace directly from your developer options on your device. Whichever solution you pick, ensure that you are collecting the Power A-Trace category so that you are able to view the device state tracks. In Perfetto Record Trace UI, you will need to enable the Power Manager A-Trace category. For this particular scenario, I've already collected a system trace using this health app for around 10 minutes of usage, and I'm going to open up the trace using the Perfetto UI. Perfetto is a platform for performance instrumentation and analysis. It helps developers visualize how their app and other processes behave. When I open up my recorded trace, there's a wealth of information displayed on screen. Don't worry, while a lot of this information is super interesting, there's only a few tracks I'm going to focus on in this talk under the group device state. I'm going to pin the tracks screen state to understand whether the screen is on or off, top app to understand which app is visible, long wake locks to see the wake locks with durations longer than a few seconds. Also, if I wanted to debug scheduled tasks using WorkManager or Job Scheduler, I can pin the track jobs. Looking to the right of these rows, you'll see a bunch of colored blocks with time-bounded operations. Each one dictates the name of the event and when the event started and ended. In Perfetto, this is called a slice. I can navigate the trace using the WASD keys or my mouse to zoom in on a specific timestamp. Narrowing down on the long wake locks track, it looks like both Health App Sensor Wake Lock and Health App Location Wake Lock have been running for a long time. As mentioned previously in the talk, when I'm receiving location data points, a brief wake lock is held at the time of receival. I can instead store the location data points to process at a later time so that I can avoid acquiring a long wake lock for the entire duration of listening for location updates. The sensor wake lock is held when the app is collecting data from a high-frequency sensor, such as sampling accelerometer data. Instead of holding a wake lock for the entire duration of the sensor collection, I can hold a wake lock for short bursts and leverage the sensor batching API to collect sensor data with longer wake-up intervals. By introducing these new optimizations, I made some great improvements to my app's wake lock usage. Here's what the system trace of my app looks like with the optimizations. We see a lot fewer wake lock blocks. While using the Perfetto UI is helpful to visualize wake lock information, it isn't scalable if I collected many traces. So I'm going to show you a feature in Perfetto that allows me to run SQL queries to help identify problem areas faster. To find all wake locks sorted by duration, I'm going to run this particular SQL query. First, select the slice name and slice duration, converting from nanoseconds to milliseconds. Then join with track on the track ID and select the track name as well. We're going to filter by only wake locks from the track named wake locks. Finally, we'll sort by duration. I can now go back to my Perfetto trace, click on the Query tab, and copy and paste this SQL query to figure out the longest duration wake locks. The top duration wake lock names here are the ones I should investigate further. I have one more tool to talk about. You may have noticed that many tools I suggested here are for debugging while manually using the app. What do I do if I want to debug a particularly hard to reproduce issue in production? This is where ProfilingManager, a new platform API introduced in SDK 35, comes into the picture. ProfilingManager is a programmatic API that gives developers more control by providing developers with a start and end trigger for profile collection. It has the ability to record multiple profile types, but we'll just focus on system trace type for this video. This will not profile every user session. The system will add additional rate limiting to ensure that the device performance is not impacted while the profile is being collected. To initiate a profile recording, I'll need to first import the Android X tracing library and core library. Then I define a consumer listener to listen for profile result completion. Once the result has returned and there are no errors, the profile will be stored locally on the device, and the profiling result will provide the path for where the file is stored. I can then choose to upload the profiling result to a server for additional analysis or define a set of conditionals for when I should upload the profile result. Now let's trigger the profile. I suggest calling this trigger where you would anticipate heavy wake lock usage. For example, right before acquiring a manual wake lock. Call the request profile and use the builder pattern to build the system trace request. Set the buffer size, the maximum duration of the profile, the fill policy, the identifying tag, and a cancellation signal. I'll also need to provide an executor, which is what thread the work should run on. To stop the profile, I would call cancellation signal.cancel. When you're locally using Profiling Manager, it may come in handy to use these debug ADB commands. One command to disable the rate limiter and collect every profile, and another command to enable unredacted files containing system information. The profile will be stored in your app's files directory. When you're debugging locally, you can choose to pull this trace using the ADB command. When I open the trace collected using Profiling Manager in Perfetto, the trace will look similar to what I previously recorded manually. However, with the caveat that this trace is in the redacted trace, it will not contain information about other processes that are not created by the app, including system processes. Only manually held wake locks by the app will be seen in the redacted versions of the trace. You can figure out how to get started using Profiling Manager with our newly published documentation. That concludes this talk on how to optimize your app battery using the App Vitals wake lock metric. We learned about the new excessive partial wake lock metric and how to leverage best practices, including consider alternative solutions, naming the wake lock correctly, always releasing the wake lock, and reducing periodic wake up frequency. We also learned a number of tools to debug wake lock usage, including the background task inspector in Android Studio, system trace collection, the Perfetto UI, SQL analysis, and in-field collection using Profiling Manager. That's all from me. Check out the video description for links to the resources on everything I talked about. Thanks for watching.